Hello everyone, my name is Daniel Parker, and today I will be presenting my project lab, which I have called Frankenstein's Bike. My main goal of this project was to put electronic gears on my bike, and I was going to accomplish this by putting a strong servo on my bike and using that to actuate the already existing components that were on my bike, which are the rear mech and the gear cable. Later on, I also decided that I would make an automatic portion, which would test the cadence of the rider and switch gears according to how fast or how slow they were turning the pedals. The general components of this lab are the Arduino, the large breadboard and the small breadboard, 2 buttons, 9-volt battery to power the Arduino, a battery adapter, 2 resistors that are both 10,000 ohms for those buttons, a mounting board for the Arduino and the breadboard, obviously various wires of different colors and lengths, duct tape, and zip ties. The specific components of this lab are the servo, which is an HS 850BB giant scale servo motor, a battery pack which was 6 volts to charge that servo, a magnetic sensor which was a Wagoneer KY003 magnetic sensor module, and magnets to trip that sensor. This lab has 3 main subsystems. The first subsystem is the main portion of the circuit, which includes the wiring of the Arduino and the main breadboard. That includes also the buttons for the manual gear changing and the integration of the other subsystems. The second subsystem was the servo and the batteries that powered it. This had to be a very large servo, as the cable that it would be pulling could be under considerable tension, and this servo would be changing the gears. As the servo pulls and releases the cable, this pulls and releases the rear mech, which changes the gears on the bike. The final subsystem is the cadence testing system, which includes a magnetic sensor and magnets. The magnetic sensor was attached on the down tube near where the crank swings by it, and magnets were attached to that crank arm so they could activate the magnetic sensor every time they pass by. This subsystem helps determine the cadence of the rider by counting the revolutions of the cranks, allowing the system to change gears when needed. These are the manual gear shifting codes. The most important things to see here are the array that's used to determine the degrees that the servo will move, and both of the if statements that are connected to the 2 buttons that shift the gears up and down. So we'll see here, as I turn the pedals forward and start pushing the gear up button, the servo will pull the gear cable and actuate the rear mech to go up in gears. And on the way back down, I'll push the other button, which will release the gear cable and allow the rear mech to return to the starting position. This is the code for the automatic gear shifting. This code is fairly similar to the manual code. The biggest differences are that it's on a timed loop, so that if statement with the current millis minus the previous millis basically starts a loop every time the current millis is greater than the previous millis. And then that loop ends when the previous millis is equal to the current millis, when it's equal to the current millis. And then inside that loop, every time that the cadence is greater than or less than a certain amount, it will change gears. So we see here that we're going to be testing the automatic gears now. So as I pedal, and I start off with no speed, it's not going to change gears at all. As I pedal faster and faster, it's going to change gears up and down. So when you're pedaling slower, under a certain cadence, it's going to change up gears. And when you're pedaling faster than a certain cadence, it's going to change down gears. And when you're pedaling in the middle of those 2 cadences, it's going to not change gears at all. So you can see now I'm pedaling faster to get it back down to the bottom of the gears.